Hello everyone. So I come from TU Delft, and today I'm going to present the software stack we are currently developing to help you actually run the quantum applications that we're presenting today. Brief introduction. My name is Sacha Bernheim. I just started my PhD at TU Delft like in January, and also just recently started my quantum journey. I only recently started quantum like a year ago. Before that, I was a cloud engineer in the classical setting. And even before that, I was just a blockchain enthusiast running a small network in his school. So I'm really excited to be here because we are at a crossroad of everything I'm passionate about. As I said, I only just recently started at TU Delft, so most of the work I'm going to present today was actually done before I arrived by this guy, Bart, who will defend his PhD in like 3 weeks, on the work I'm presenting. And all this work is done under the supervision of Stéphanie Wehner. So Julien just talked about the Quantum Internet Alliance, this big European project. She is the head of the project, and I have the great chance of working under her supervision. So in Stéphanie's group, we work on many things. So some of them are quantum applications that we can run on a quantum network, but that's not what I'm working on. I work on another goal, which is make available to so the idea is to make sure that we can run any quantum application that we see today from high-level software without needing to understand any of the physics behind it. If we think, for instance, of when we code things in the classical settings, you don't want to have to understand how any of the AMD x86 architecture or RRM architecture work, or even how do they manage to communicate between each other. Well, we kind of want to do the same thing for quantum networks. We want to make available, we want you to write an high-level application, and then it can run on the different hardware, and you don't have to have like a PhD in quantum physics to understand how it works. So those applications will run on the network. So this is a brief overview of the network. The idea is that on the physical layer, we have the quantum platform, which can share entanglement. On top of that, we have a quantum platform independent stack, which allows to have some classical message passing. And on top of that, we want to put our software stack. The role of this, so it's not a black box, it's a green cloud of the network, is to be able to generate entanglement between any two nodes, any two end nodes in the network. In the middle of that, there might be other nodes like quantum repeaters. We've heard a bit about that. We're not interested in that here. We are really interested in the end nodes which will run the applications. Also, to understand a bit what an application is, the application is the overall protocol that you want to run. For instance, we've heard about QKD, VBQC. So that's the application. This application is separated in 1, 2, or n programs, and the programs are what are actually put and run in the node. So we just agree on the semantics I'm going to be using for the rest of this talk. So once we understand this, the first brick that was actually developed is called QNode OS. So it's the first quantum network operating system, and it works a bit like this. So we have like this first block, which is the classical network processing unit. So this is where we will input the user program, not application here, and this user program would be sent to the runtime. And so if there is any classical thing happening in the program, this is where it will run. And when it sees some quantum instruction, it will go to the coprocessor driver, which will send that to the QNPU. So the QNPU is the quantum network processing unit. Despite its name, it's still a classical system. We're not at the quantum level yet. And so this is what will communicate with the real quantum device and send what we want to run on the quantum device, and also will be responsible for retrieving the results after the measurement. This system was actually realized on real hardware, where it was used on 2 nodes to run a small delegated computation. So this works in real life. And also was demonstrated on the real hardware some multitasking abilities, where one node would send this computation to another node, and in the meantime, waiting for the results, it would run like another computation. So we really are reaching the level of a real network at this point. However, this is still a bit limited. So as I said, we managed to run some multitasking with that, but it's very limited because the CNPU and QNPU both have their scheduler, but there is no like overall scheduler, which would be helpful to have some more efficient multitasking capabilities. Also, as I said here, we only have a runtime, which means that we feed a program and it's executed. We don't have like any compilation or optimization happening beforehand. And so that's what why Koala was introduced, which is kind of a framework extension to QNode OS. So Koala is developed as a software development kit. So in here we have a simulator, and we are currently building a compiler. And so once you write your application with the Koala SDK, the compiler will output a set of programs. Those programs are actually executable files that are defined in the Koala paper. And they are built around different notion of blocks. So the blocks define if the next instruction we want to run is a classical local operation, so just for instance an addition, or is that a quantum routine, or is that an entanglement request, or are we sending a classical message? Those programs, they will be sent to the nodes, where we have this new task scheduler, which is aware of what's happening both on the CNPU and the QNPU of QNode OS, and so is able to integrate more efficient multitasking capabilities. And then this program is then sent, the task scheduler then decide which block to send to QNode OS for execution. So now I can talk a bit about what I'm doing in the group, now that we understand that. So for the next 4 years, I will work on the compiler that we are currently building. So as you probably all know, the idea is to have like this really high level software language, and then at the end of the pipeline of the compiler, just have the Koala executable file, which is basically some assembly level language, and you don't want to have to write that. And also working on the optimization passes that are happening here. The hope is that since we are at this, we have this new thing where we have like 4 computation capabilities, as I introduced. So the classical local operation, the classical communication operation, the quantum local operation, and quantum communication operation, that leverage all this, some new optimization opportunities will arise. And other PhD students in the group are working on some other parts of the system. So the first one, the task scheduling, so I just introduced that, and also the network scheduling, which is part of this kind of green cloud I put there. The next course, network scheduler, is the component which decide when 2 nodes can generate entanglement. It like distributes some time slots where you can generate entanglements when needed in your application. So thank you for listening, and if you have any question.
I guess. What type of license is there on QNode OS?
I don't know. I know that some of the softwares that are developed at QuTech are under MIT license. I don't know for QNodeOS. But you can find the code on GitHub, so you'll probably find a quick answer to that.
If I may, if you go to the QNode architecture, can you give me a bit of intuition why the quantum network processing unit is needed? Why can't you already have a specific classical network processing unit? Why doesn't it just send instructions immediately to the quantum device?
That's a good question. The idea was we did not want to do too many things here because there is like some translation step that needs to happen. So I said that the stack needs to be kind of hardware independent. Well, actually, this link here kind of depends on the hardware that you're running underneath, because some types of gates are only available to some types of device, and so here is where kind of the translation magic happens.
If I buy a new quantum device, it should come with sort of a new quantum network processing unit, most likely.
Yeah, or at least like. So the idea now is that we will integrate this in the compiler. So meaning that when you will have like a target architecture, all the translation will happen there. And so you won't need the new, but this is also the thing that is able to interpret the assembly level language of for quantum routines, which this one is not capable of. The idea was also to have like something as modular as possible in case we need it.
Can we develop application and deploy them on, as this being used on like live systems or only on simulations?
So QNodeOS has been run on live systems, as I said, in the paper which presents the thing which has been published in Nature. We show the experiment that was run, where there is a small quantum delegation computation happening here with only 1 qubit, but still.
But what hardware can we use it? On which hardware can you use it now?
So the experimental realization was done on NV centers. I think also that there is the translation that is also available for trapped ions, but it has not been done experimentally yet.